And yeah, his advisor originally so. But anyway, so yes, talking. So how about I let you get started?
Okay. Do you see the slides?
Yes.
Okay, great. Thanks for arranging. I'm Docking Lee. I'm going to talk about thermal analysis of Neo-Pascal. Okay. Yep. I'm going to introduce the Neo-Pascal mission and the original Pascal mission, and then I'm going to talk about thermal analysis and results and discussions. So the original Pascal mission was actually proposed about over 20 years ago. And they tried to send to Mars several micro-meteorological landers, which was actually small at the time. And the main object of the mission was to validate Mars General Circulation Models, GCMs, by measuring global surface pressure. The importance of the measurement of the global surface pressure is our current knowledge on the in situ data is very crude. It's like attempting to characterize the PBL, which is a planetary boundary layer structure of the entire Earth based on measurement at just 3 or 4 locations in Sahara Desert and in northern Canada. So currently there are only 2 operating meteorological stations on Mars. Those are RAMS, the Curiosity, and recently landed InSight lander. So the Neo-Pascal mission is a modern revision of the Pascal mission. Currently, it is a conceptual design. We don't have fund yet, so we hopefully apply for the funding in the future. The major differences between the 2 missions is size and mass. Thanks to recent progress in miniaturization of the technologies, we can use CubeSat and some kind of commercial off-the-shelf coach components, so that we can reduce about 10 times of the mass from the previous mission. By doing so, we'll be able to send a more number of stations, and as a result, we will be able to do better and strong science in the future. However, there are several challenges, something like thermal and structural and electrical and EDL, which is entry, descent, and landing. However, in this study, I will focus on thermal design, and the everything other than that will be covered in further studies. So, purpose of this study is to assess the feasibility of the thermal design and thermal model of the Neo-Pascal mission through thermal analysis. The second section is about thermal analysis. And first of all, I want to talk about thermal environment of Mars. The landing station will exchange heat with environmental factors, for example, sun and atmosphere, and cold sky and ground as well. And the values of the thermal environment, something like temperatures and solar flux, those vary mainly according to landing site latitude and seasons, which can be defined by LS, which is solar longitude. This figure shows solar longitude. And in northern hemisphere on Mars, when solar longitude is 90 degrees, it is summer. And when it is 20 to 70 degrees, it is winter. And in our study, we will see the worst hot case and cold case, assuming that the lander is landed at southern hemisphere. So we chose the worst cold case, which is winter, at solar longitude is 90 degrees here, which is a little colder than this northern winter solstice. So those are actually the worst cold and hot cases. And these profiles are the simulation results from the Mars climate database. And as you can see in the left panels, for the worst hot case in summer, the temperature of the environment sometimes goes above room temperature. However, in the winter, most of the temperature goes below minus 50 degrees Celsius. So this indicates that we need enough heating power for the successful mission. And in order to obtain enough heating power, we should get more solar flux. That is natural. However, as you can see in the right panels, in the right bottom panel, those values indicate solar flux at surface according to the Nixide latitude. So when it is minus 30 degrees, the peak goes like over 270 watt per square meters. However, when the latitude goes down to minus 50 or 60, it greatly decreases. So in this study, at first we wanted to assume the landing site latitude to be plus minus 30 degrees. And we performed thermal analysis for two models. First one is board set-based model, and second is cube set-based model. And those platforms have been recently used by other researchers, and the CubeSat platform is widely used at the moment. And this figure shows the board set-based model. And as you can see here, there are several components, and it is very simple and very simple model. And it contains very essential components like batteries and pressure sensor here, and antenna and PCB. And in the right panel, you can see some thermal structures, something like aerogel and insulating spacers. And for aerogel, we want to use a flexible one in order to avoid any damage or crack, because launching and landing environment will be very harsh. And the aerogel's thermal conductivity is very low. We also use the insulating spacers. Actually, the spacer is made of aluminum, which has quite moderate and high thermal conductivity. But by inserting G10 washers, which has low thermal conductivity, we can greatly decrease the effective thermal conductivity. And those insulating spacers will be mounted to the corners and its structures. And I want to show about a new design concept, which is a large sail. Basically, this sail is for soft landing of the board set-based lander. As you can see here is board set-based lander. And the great advantage of the use of this kind of concept is that we can utilize a large area for the flexible solar cells. So we want to use some commercial solar cell, flexible solar cells to maximize the power generation. And those kind of concepts were already demonstrated by other researchers. Something like Chuda and colleagues demonstrated deep space solar cell, which was, and they attached thin film solar cells on the sail and something like that. But we have a different purpose. Our solar cell is mainly for landing. But the detailed structure and design of the EDL is not covered in this study. So the second model shows the cube-based model and the components here. And you also use aerogel and insulating spacers as well. And this table shows the power budget of the board set-based model. And we calculated assuming 10% margin from the power consumption. And as you can see here, negative means the consumption. So power consumption of the each component and one solar energy. One solar means one solar Martian day. One solar energy is calculated like this. And the solar cell performance of these values were calculated using the total area of 0.84 meter square of the solar cells and the efficiency of 8%. And this table shows the values of the CubeSat-based model. And I calculated those values with the same method. And I don't want to go into detail in these slides, but I just want to say is in the calculation of the energy generated by solar cells, we assumed winter season and we used flexible solar cells and action schedule, and also we we applied dust substitution effect at 90 sols, so about 30% of deposition. So this value, 1724 watt hour per meter square, is calculated by the is same as the area of the solar flux of the solid line. And the dust substitution rate was this dust substitution of the 30% was calculated using the dust substitution rate of about 0.3% per sol. And using the previous values, we also calculated the generated power in winter and available power in winter. I wanna, those values. And those values were also calculated by assuming 20% of margin from the heating power here, and 20%. And we also assume that there should be always remaining battery power level about 20% and every morning, just in case and for emergency. So we use those kind of several margins just in case. So the finally calculated heating power of the BORSET-based model is 2.3 watt, and that of CubeSat-based model is about 0.6 watt. The reason why the heating power of the BORSET-based model is larger than the larger CubeSat-based model is the use of the large area of the solar cell. And this table shows the input parameters, something like density and thermal conductivity and thermal optical properties of the each component according to their materials. And we also calculated thermal conductance values between two joint surfaces. And I want to skip this part. And I also calculated gaseous conduction between PCBs and some components, because there's thin gaps between the layers and the PCBs. And so I used the CO2 thermal conductivity for various temperatures, as you can see in the table. I also used kind of extreme convective heat transfer coefficients based on the literatures, and also albedo here as well. So the results. The first result shows the temperature of the pressure sensor. And the right panel, as you can see here, it is the result of the CubeSat-based model. 4 different aerosol blanket thicknesses, which is TA here. And as I said, pressure sensor's temperature limit is between -25 to 85 degrees Celsius. And as you can see in the right panel, CubeSat-based model does not satisfy the requirements for every thickness, here 15, 30, and 45. However, the results of the BORSET-based model the thickness of the aerosol of over 20 millimeters, it satisfies the requirements. Even in the case when I add the error of the analysis about 10 degrees Celsius, like this dotted line here, and the this dotted line in the bottom here shows the same results with the smaller heating power, not 2.3 watt, but 1.05 watt. And this indicates that we absolutely need enough heating power in order to survive on the Martian surface. So our analyzed aerosol thickness is slightly thinner than the aerosol which will be used in the Mars Helicopter Scout, which will be deployed from the Mars 2020 rover. The second result shows the temperature of each component. And I used a single aerosol thickness. And as you can see in the right panel, CubeSat-based model of the 15 millimeter thickness of the aerosol, it does not satisfy the requirement, especially in winter. However, the BOSET-based model, every component satisfies the temperature requirement, and each of the temperature is above about 15 degrees Celsius from the requirement. So I think that is quite our model, thermal model is quite robust. These figures show the temperature distribution at the coldest moment, which is nighttime in winter, what's called case. And the outer structure of two models have very low temperature. However, in the left bottom panel, the inner component's temperature of the BOSET model, BOSET-based model, has quite good temperature range within the temperature limit. Even though the result of the CubeSat-based model does not satisfy the requirement. However, we can see the effect of the use of the insulating spacers here, because each temperature of each PCB is discreted. And finally, I wanted to see the effect of G10 washers. So I compared the result with and without the G10 washers. So this is the previous result with the G10 washers. The same solid line indicates the same result. And in the bottom right here, the dashed dotted line indicates the result without G10 washers. And as you can see here, the result, the temperature decreases about over 35 or 40 degrees. So this indicates that the use of the G10 washer is very important in our thermal model. Okay, so discussion. So what specific sciences with the NeoPascal mission we can have? It depends on the landing site latitudes, basically. In our study, we limited the landing site latitude between plus minus 30 degrees. This table shows an estimate of the minimum number of surface stations, here capital N, and their distribution required to study various atmospheric phenomena here. So here you can see there's not many topics we can do with this plus minus 30 degree latitude limitation. For example, we can do equatorial waves. We can study equatorial waves and something like mesoscale system. And we can maybe study those storms here because it requires two stations at 35 degree latitude. And I want to talk about the feasibility of our thermal model. The thermal model of our study is quite feasible, and it, based on the thermal analysis results, will be survive in any season for over at least 90 sols, only if it is landed on between plus minus 30 degree latitudes. And the reason why I said our thermal model is quite robust is we assumed several margins, and some of the margins is quite too tight. For example, we used solar cell efficiency of about 8% for the ball set-based model. However, there are several brand new flexible commercial flexible solar cells which has over 14%. So for the future work, I want to increase the landing latitude up to 40 degrees or even more, like 50, by using better commercial flexible solar cells, which has higher efficiency, and by using larger area of the flexible solar cells. So the solar flux, which is expected to be received at the Martian surface at minus 40 degree latitude, would look like this. However, if we increase the solar cell efficiency over like 75% from 8 to 14%, then we'll be able to cover the missing solar power. So this map shows the Martian surface, and light blue colored area shows the possible landing site latitude of of this study. However, in the near future, I hope to increase the possible landing site up to 40 or even 50. So by doing so, the sciences that we can do with New Pascal mission will be more, I guess, including the storms and barely mid-latitude waves as well. So this is summary. I chose thermal modeling and visuals, including many options and conditions with margins, and we found that the thermal analysis visuals show that the model, especially the ball set-based model, will be surviving in any season at landing latitude between plus minus 30 degree for at least over 90 sols. And I hope to increase this kind of limitation larger. And Mars meteorology, the NeoPascal lander will be able to study these studies. Okay, thank you.
All right. Thank you for the nice presentation. Are there questions from the participants? So if there are none, then we would, yeah, let's thank you, Larkin, for the great overview of this ongoing research in NeoPascal. It's very interesting. Should we then just go to the second speaker? Are you in the same room actually?
No, I'm not in the room with them.
Okay. All right.
Can you see my presentation there?
Yes.
Okay.
All right. So the next presentation is by Samuel Clemens. So you are a PhD candidate at your
Master's of Science.
Sorry?
Masters of Science.
A Master's of Science. Okay. And you are in your second year now?
Yeah.
Okay. All right. So this presentation is going to be slightly shorter. So we kind of aim for like 10 to 15 minutes. And Samuel will speak about the feasibility for using commercial star trackers for on-orbit resident space object detection. Okay.
All right. Thank you very much. The broader topic of my work is space situational awareness, which is becoming a bigger issue or bigger area of study in recent years. Currently, there's just under 20,000 objects being tracked by the Space Surveillance Network, which is the United States network of sensors that track objects in orbit around Earth. And the risk of collision between objects is growing, and that threatens to damage either active satellites, or if it's two inactive satellites or pieces of debris, that will increase the debris population further if there's a collision that occurs. A resident space object is just essentially any object that's in orbit around Earth. So that could be active satellites or inactive satellites, or some sort of debris, whether it's mission-related debris like a lens cap or something that's separated from the satellite, or a rocket body that's deposited its payload and just in orbit now, or some sort of fragmentation debris. And in the figure there, you can see that the total number of objects in orbit around Earth was steadily increasing. And then in 2007, there's a huge jump there, which was caused by an anti-satellite missile test. The Chinese blew up one of their an old weather satellite, and that greatly increased the fragmentation debris. And then in 2009, there's another slightly smaller jump, which was a collision between two satellites, Iridium and Cosmos, I believe. And so those are just two examples of, the Iridium Cosmos collision is an example of what happens when two objects collide. One, it destroys active satellites, and it increases the debris population, making the problem even worse. So currently there's both ground and space-based sensors that monitor RSOs, resident space objects. This is an image of all the sensors being used by the Space Surveillance Network. They have mainly radar and optical telescopes based on the ground, but they also have some space-based sensors. You can see in the image there, SBSS, space-based space surveillance, and the GSAP satellites, which I believe are for observing the geostationary belt. And Canada also has two of its own satellites which monitor RSOs, Sapphire, which contributes to the Space Surveillance Network, and NeoSat, which I don't think contributes to the network in the database, but it still searches for RSOs. But despite all of these efforts, there's still gaps in both the spatial and temporal coverage that we have of RSOs. And so one idea or one thought is to use star trackers to monitor RSOs. Star trackers are used for attitude determination. Essentially, you take an image of the stars and you can tell which way your satellite is pointed. And so these are used on a lot of satellites right now. And so the thought is that they may provide an additional source for RSO detection. It's not intended to replace anything. It's not going to replace radar or optical telescopes on the ground, but it's just meant to complement them and provide an additional source of RSO detection and updates. And so that's what Magellan Aerospace, they're co-funded by the CSA's STDP program. They're seeking to do that. They're designing analytic and machine learning algorithms that will detect RSOs within star tracker images. And that is where I come in. So my objective or my task was to perform a feasibility study of commercial off-the-shelf star trackers and their ability to detect and identify RSOs. So some of my goals were to determine the number of RSOs that would actually be detectable by a star tracker in orbit around Earth, how many objects are you actually going to see, I also modeled some of the effects that different star tracker and mission parameters have on detection rates, mainly the orientation of the star tracker. So how does the direction you're pointed affect the number of objects that you see? And I also simulated star tracker images to verify Magellan's detection algorithms. So star tracker images generally aren't downloaded to the ground, and when they are, it's not the whole image. It's just regions of interest. So for them to actually test their algorithms is difficult on real star tracker images. So one of my goals was to simulate images that they could use to train and verify their algorithms. So Magellan's, their goal to consider this project actually feasible was 1 to 10 RSO detections per star tracker per day. That was just the useful minimum that they came up with. Over a 5-year mission, if you detected 1 object a day, that's 1,825 total detections. And so you're updating somewhere between 1 and 10% of the catalog over a 5-year mission, although they expected much higher rates. So the way that I did these things was through a couple different simulators. One was an analytic simulator, and it estimated detection rates. So given this star tracker and these parameters, like these characteristics of the star tracker, and in this orbit looking in this direction, how many objects are you actually going to see? How many resident space objects? And so the simulator uses the TLEs, the two-line element sets of RSOs in the host star tracker satellite. And these two-line element sets just contain all of the information needed to recreate the orbit of a satellite. So using this information, it propagates the orbits of the RSOs over a specified amount of time, and it determines how many objects the star tracker will actually see. It spits out 4 parameters at the end, 2 accesses and 2 detections. An access is any time that an RSO crosses the field of view of the star tracker, and a detection is when the RSO is close enough, big enough, and bright enough to actually be detected by this star tracker. And then the terms unique and total just refer to, well, unique is the number of unique individual objects that you detect, and then total is taking into account repeat detections of the same object. So it spits out these 4 parameters as the results of the first simulator, the analytic simulator for estimating detection rates. And the second simulator, as I mentioned, just simulates images so that Magellan could test their RSO detection algorithms. And again, because star tracker images aren't readily available, the simulator was validated using the fast auroral imager on board Cassiope. That's an image of it there, or one image of the FAI sensor on the right there. And I'll show some sample simulated images later on. But first, these are some results from the analytic simulator. So I ran a few different simulations with commercial off-the-shelf star tracker parameters that you can see on the bottom left there. And I ran that with different orientations of the star tracker. So I looked at 4 different orientations. So a RAM and anti-RAM orientation, so looking in the direction that the satellite is moving, and in the opposite direction away from the direction or the velocity of the satellite. And I looked at those 2 orientations because if you're in a polar orbit going from the North Pole to the South Pole, as you come up to the pole, you're looking at the place where all of the other polar orbits are intersecting. So you'd have a high, or we suspected that you would have a lot of detections as you come up to the North and South Pole, and seeing where all the other polar orbits intersect. I also looked at a zenith orientation, looking directly away from the Earth, because that's star trackers are typically pointed away from the Earth. So that was intended to kind of simulate what like a regular star tracker would see, not being used for RSO detection, but being used for attitude determination like it's intended. So just to see how many objects you would see with a regular star tracker doing its normal thing. And the last orientation I looked at was an anti-sun orientation, so just looking directly away from the sun. And I looked at that because it gives the best viewing geometry. So with the sun directly behind you, you have the light reflecting off of the RSO in front of you and coming right back to you. So it's the best viewing geometry, or gives you the brightest objects. And so the results are there in the table. The most important results are the total detections and unique detections, which are highlighted or a little bit darker in the bottom. And well, long story short, you get we're seeing a lot more detections than the 1 to 10 goal that Magellan had specified. Even the zenith facing orientation, which is the worst out of all 4 that we looked at, it's seeing at least 40 RSOs in a day. And then the anti-sun and RAM are seeing over 3,500 detections a day. So this is a good sign, suggesting that we will we'll see way more objects than the minimum usefulness that Magellan suggested at the beginning. The image simulator, I'll just give a brief overview of it and show some example images just to get an idea of what it does and what it's capable of. So the image simulator obviously simulates stars and RSOs. It uses a point spread function to simulate those. There's a point spread function of a star on the bottom right there. And it simulates the motion of both the RSOs and the star tracker. It simulates the Earth and the Moon, as well as reflected solar light from the Earth and the Moon, which causes like background noise and makes it difficult to detect RSOs. Background radiance, and then a bunch of noise sources as well, so hot pixels and dark current, non-uniformity in these noise sources, as well as a DC offset just intended to make the images as close to level 0 as I could. These are 2 simulated images just showing the different exposure times. So there's a lot of information in the header, in the headers up there. But on the second line, it has, on the image on the left, the exposure time is 0.1 seconds. And on the image on the right, the exposure time is 10 seconds. And this is just showing when you have a longer exposure time, the stars begin to streak and you have more noise. These 2 images are showing the Earth and the Moon. The Moon is on the left with light reflecting off it and causing a glow. And the same thing with the Earth on the right. The Earth is in the bottom left. It's that dark gray part. And then the white strip is Earth glow, reflected light coming off of the Earth and through the atmosphere and being scattered into the star tracker. And that extends about 100 kilometers from the surface of the Earth there, as far as the atmosphere extends. This is an image which has 30 RSOs in it. I don't know how easy that is to see. The next slide has a zoomed in or zooms in on a couple of the RSOs, but I don't know if you can see my mouse, but there's one here, and 30 others. Whether or not they're visible to the eye, they're in there somewhere. And so Magellan's algorithms will hopefully be able to pull those out of the image. So here, zooming in on them, you can just see all the stars are streaking in one direction, and then RSOs are typically going in other directions. So those are two RSOs there. To verify that the image simulator was actually working, I compared images with the FAI sensor. And so on the left there is a real FAI image, and then on the right is my simulated image of that exact same image taken at the same time with the same parameters and the same orbit and all that stuff. And so thankfully, when I actually simulated the image, an RSO popped up in about the same place as it should. And so that's, I was able to identify which RSO it was, and that's an image of it on the bottom there. I think it's a Russian weather satellite, Meteor 129. And so comparing with the FAI, I was able to compare the position of the RSO as well as the brightness to verify it and quantify that it's actually, that the image simulator is actually working properly and doing what it's supposed to do. And I also compared with just this final image here. Same thing, this is a rocket body FAI image on the left, the simulated image on the right at the same time, same parameters. One thing to note, the RSOs, all the RSOs are simulated as spheres. So the rocket body was simulated as a 16-meter sphere, 16-meter diameter sphere, just to simplify some of the calculations and things that the simulator needs to go through. So this rocket body was simulated as a 16-meter sphere, and it shows up in about the place that it should. So in summary, the analytic simulator, which estimates how many objects you'll actually be seeing, is suggesting that a star tracker will see way more than 1 to 10 objects a day, which is a good sign. And the image simulator was verified and is producing at least semi-realistic images. And it's currently being used by Magellan right now to verify their algorithms, and it's being taken a step further, and they're going to be doing light curve analysis on the images and stuff like that. Thank you.
All right, thank you, Samuel. All right, are there questions from the participants? If not, actually, I have one.
Sure.
On one of the first slides, you showed these collisions by like the Chinese test, and then there were also like another collision between two satellites.
Yep.
For how long do these the particles that are coming out of this? For how long do they stay in a very similar orbit?
So that would depend, and so there are people who are looking into, well, how long does debris actually stay up there, and when there is a collision, what actually happens? Does it stay in the same orbit and stuff like that? I can't speak too much on what actually happens once it's created. So there are whole studies occurring on what actually happens when there is a collision. So I can't speak too much on that.
Okay. But I mean, you would expect, at least because the velocities of the orbits are really, really high, that even if you change, let's say, by tens or hundreds of meters per second, you still kind of are in the same orbit after the collision.
Yeah. And it would also depend on how they collide. So whether they're in similar orbits to begin with and then they collide, they might stay in a similar orbit, but if they're like going cross track with each other, which would be a lot less likely, but if that were to occur, if they're going cross track and then they collide, I would expect fragmentation debris to go every which way.
Yeah. And I guess another question that I had is, like, when you do, I mean, you do the simulator, you purely simulate images like that you try to put in as many of the noise sources as possible. Is it not possible to simply add signals into the real data and then let them, and then check whether the detection pipelines find them?
You mean rather than using like actual RSOs? I
guess aren't they like, I mean, there are two goals, right? One is kind of to keep track of the RSOs, but also maybe to discover new RSOs, no? Or what is it?
Yeah, so part of it, like when this is actually being used, part of it is to, to update the catalog. So you image a satellite and you can determine its orbit, and then you compare it with the catalog, and you can determine, okay, this is an object that we've already seen and we're updating the orbit. Or if there's nothing to compare it to, then I think it goes through a process, but eventually it's cataloged as a new object. Is that?
Yeah. So I guess my question is, why not just use the real data and artificially add signals into the data and then check whether the pipeline discovers those artificial objects? Because that would be like a more realistic test, no?
So I'm not sure I understand your question. What do you mean using real data and then simulating a signal?
Well, I'm just saying, right now you're making up the data completely from the beginning, and you're trying to simulate all the stars, you're trying to simulate the exact view, but why not take existing data and inject signals, tiny little signals like that are your RSO, what you would assume the RSO would have caused if it was there. And then these detection pipelines could run on the real data and see whether they find your injected signal.
So you mean rather than simulating the image as a whole using a previous image and then like adding an RSO into it?
Yes.
So that, well, one of the problems with that may be possible. One of the problems is that actual star tracker images aren't really readily available. They don't usually download them to the ground. So that's why I was using the fast auroral imager. It's similar to star trackers, but it's not the exact same. So
yeah, but for example, why not use that data and inject signals?
So I suspect that could have been done.
I mean, it would still require kind of the same work, but because you would still need to, you would still want to put some kind of realistic RSO in, and you still have to calculate exactly where in the image that would fall. It's still a very challenging task, and I think many of the steps that you have done would be still necessary in that case as well. But at the same time, you would have, I don't know. I mean, that's what we're doing all the time. For example, for exoplanet detections, if you want to understand how sensitive your detection pipeline is, one really good way of doing this is to inject artificial signals into the real data and see whether the pipeline finds them, so then you can basically say, given these real data, I would have found this kind of planet or this kind of, in this case, RSO in the data.
Like assuming that the real data is obviously better than any simulated data I can create and simulated noise and stuff like that.
Yes.
Yeah, I didn't think of that, didn't consider that. So that maybe would be, or either would have been better or would be a good next step to compare as well.
But I think in this case, they have real data and real RSOs in it. So they could just, scan through a sample of, if the detection rate is so high, they could just sample through a set of real image and just pull out the sensitivity from it.
I think, well,
there's no shortage of RSOs in these image from what the simulation says.
Well, of which images?
Of, say, the fast auroral.
So, well, one of the issues was having a lot of data with RSOs in them. So they looked through like a whole bunch of the FAI images, but it's hard to sometimes actually pick out visually, okay, this image has an RSO, this one doesn't. So one of the goals of the simulator was to be able to create images with and without RSOs, so that you have test cases or verification cases, and you can create hundreds or thousands of them. One of the algorithms is a machine learning one, and so it needs hundreds or thousands of cases for it to do its thing, right? So that was one of the goals of the image simulator, was to just be able to create lots of images really, really fast, so that you can run it with the machine learning algorithm. Because
I guess another good application of this could be that, I mean, your simulator basically, if you could, I guess, as you showed in the last slides, you showed that you can reproduce existing images, right?
Right.
And in these reproductions, you know which RSO would have fallen, or which existing RSOs would have fallen in there. So then I guess one question to ask is, using the real image, does the pipeline or the different pipelines recover all the ones that you said should have been in that image?
So we didn't know which. So I only identified the RSO after I simulated the image. So we suspected that was an RSO in that last image. If I can get there quickly, we suspected that it was an RSO, but we weren't 100% sure. And then I simulated the image, and it showed up in the same place. And then because I took in all the TLEs to simulate it, I could figure out which TLE I used to simulate that one there, and I was able to identify it that way. So we didn't, with the FAI images, we couldn't even be 100% sure if that is an RSO in there, or whether it was, whatever it was. We couldn't be sure exactly what it was. With the simulator, you're putting in the RSOs, so okay, I know this is an RSO here, so that when it's when the algorithms are tested on this image, for sure whether or not what the results should be. With the FAI images, we didn't know for sure if that was an RSO.
Yeah, I guess that's exactly what I'm saying, right? Because now you know that this is an RSO, so the pipelines applied on the real data better finds that RSO.
Right. So you could, with what you're saying, if you use the real FAI image and then put a simulated RSO just in that real data.
I guess I'm saying two things. The first thing is you inject another signal there and it should find it. The other thing is exactly kind of what you also said, this is the second point, is that you basically now, because you can simulate the images, you know which RSO should be in the image on the left, right? And the pipeline should find those.
Right, yes.
Yeah.
Yeah.
If I can ask a question on, you said that the RSO were simulated as spheres?
Yes.
Is it a diffuse reflection, or what kind of albedo did you use on them, or?
The albedo, I think, is in general for fragmentation debris, I think they use 0.2 or 0.175. So I was using that. And it's a mix of specular and diffuse reflection. So you can actually change the amount of specular and diffuse reflection. That can be changed. I think I was using just like a 50-50.
Okay. And does your simulator takes into account like the RSO going into the shadow of the Earth and all the things like that when it pulls out the number of RSOs that you should?
It does, yeah. If an RSO is in the shadow of the Earth and there's no sun reflecting on it, then it takes that in consideration. It also does like the solar phase angle. So based off of where the sun is and the RSO and the star tracker, the brightness of the object will vary depending on that. Which is why, so that's the one test case I did was an anti-sun orientation, so looking directly away from the sun, because that gives you the best phase angle.
So then those statistics you pulled out in the 6 different simulation, are these from simulating all 20,000 objects in the catalogs?
Yes. Or I think it was probably about 13,000 low Earth orbit objects. So not the full catalog, but it was all the low Earth objects in the catalog, which was about 13,000, I think.
13,000. Okay, so you really used actual RSO data to pull out these detection limits.
Yes. Yeah.
Okay. Cool. So we're doing we asked question because we're doing at Laval a very similar project, which intent is to use a dedicated sensor to probe into.
I actually have to leave right now, but because I have a meeting at 1. But you can feel free to keep on discussing. It's just that I have to leave to go to another conference.
Sure.
Okay.
Sure. So I was saying that we're doing a very similar projects, but the intent is to have a dedicated sensor that sends very small objects that are not part of the catalog, and so we'd be very interested to maybe discuss in more detail some of the tools you've used. I guess this was a master or a PhD project?
Master's.
Okay, very interesting. So we'd be very interested in knowing a bit more. So we'll probably chat through emails after the meeting.
Yeah, absolutely. That would be great.
Cool.
All right. Are there any other questions? No? I guess we're done then. I don't know.
Yep. So we're gonna leave.
All right.